In this lecture, we'll continue learning about Foundations of Computer Science. Foundations of Computer Science, Lecture 2. Not sure how I'm going to do intros for these. So recall that last time we introduced the basic ideas of sets. We talked about the empty set, we talked about singleton sets, we talked about the union operation, the intersection operation, the complement operation, and the power set operation. We talked about alphabets, which we write down with sigma, which are finite sets. We talked about the universe as a concept. And one thing that I didn't really elaborate on is that since languages are going to be sets of strings, that means that the universe are strings of sigma, and we write down strings of sigma as sigma with a star next to it. That's the notation for that. All right. Now, the main concern that we have in this class is to define what computations are possible. So what we're going to do is we're going to name the set of all conceivable computations. We're going to give it a name, and its name is going to be all. Very intuitive name, huh? So let's write down, let's make a big box for all. Okay, so this box right here are all possible computations. Now, when we say all possible computations, that means all possible sets of strings. Okay, well, how can we write down the name, or rather a formula, for all possible sets of strings? Well, it's actually quite easy, because we know that the power set is all subsets. So if we write down sigma star, which is the set of all strings, the universe, and we write down P of sigma star, then that means the set of all possible substrings. Sorry, of all possible subsets. Now, there are some really interesting elements inside of all. So here's an example. So there are really basic things like all strings made of zeros. I'm going to write so remember how before I said, okay, well, we can have a set of this alphabet that was made up of just strings that had zeros in them. So that's an example. All strings made of zeros, that's something inside of all. Here's another thing. All strings that are GIFs. So a GIF is a file format, and so that means as a file format, it's a sequence of bits. So only some sequences of bits, though, are actually GIFs. In particular, I believe that all GIFs start off with the ASCII GIF at the very front. That was like the very first, 24 bits. Okay. Now, there are more complicated things inside of all, too. For instance, we know that we can use binary to encode arbitrary textual data, right? So we could have something like, all Harry Potter novels. That right there is an example of an element inside of all. It is a set of strings, and each string inside of that set would be one of the different Harry Potter novels. Similarly, we could have one that was like all algebra problems. For example, it would have the string like x plus 3 equals 7. Okay, that would be an example algebra problem. Now, there's another way that we can think about this, and this would really be encoded as some sequence of bits. We're not really sure what it is, but whatever. Okay, we could also have one that was all true math formulas. So a true math formula would be one like 1 plus 1 equals 2, or another one might be for all x, x plus 0 equals x. Okay? So each one of these are more and more elaborate subsets of strings. So these are all possible subsets of strings. Now, inside of this, there's a really, really small set of strings. Notice that each one of these, by the way, so this one is infinitely large because there are, you can't pick out the last string made up of zeros. There are infinitely many GIFs. There's not infinitely many Harry Potter novels, but presumably someone could keep writing more and more fan fiction. So if we included fan fiction, then it would be infinite. There's definitely an infinite number of algebra problems, because, for instance, we could have x plus 0 equals 1, and x plus 0 equals 2, and x plus 0 equals 3, so there's as many as there are naturals. Similarly, there are definitely infinitely many true math formula. So most of these examples over here are infinite. But so far, we've only told you how to make finite sets made up of empty, singleton, and union. So that means way down here in the corner is a very small piece that we'll call fin. And that very small piece down there, that piece are all the finite languages. So that would have things like, pen and tablet. Okay? So right now, this is the picture that we have of all possible computations. We've got all, which is everything, and then we've got fin down here. Now, there's obviously a huge gap between these. In particular, we don't have a way of writing down a language, i.e., a set of strings, that is infinite. So let's make that our very next task. So we want to write down at least one infinite set of strings. Now recall that there can be many different representations of the same kind of thing. So for instance, we had the pen tablet way of writing down that set, and we also had the picture version where I drew a picture of a pen and a picture of a tablet. And these are both different representations of the same set. So it's not the case that every way of writing down a set always has a little brace and then a list of things. In particular, we know that these are equivalent. We could say pen, union, tablet. Okay? So we can write down the elements, we can use a formula, or we can, maybe draw a picture for part of it. So what we're going to do now is we're going to write down the set of strings that are made up of only zeros. So we'll call this only zeros. So I'm going to write down this set inside of this box right here. All right? And here's the picture of it. So I have an arrow coming in from outside of the box, and it's pointing right here to a circle that has a circle around it. Then there's an arrow goes back to it labeled 0. And then there's an arrow labeled 1 that goes to here that has one edge labeled 0 and another one labeled 1. So this right here is a set. Now, you may be thinking to yourself, that doesn't look like a set. I mean, I thought all sets had these braces in them. But remember, there are many different representations for the same ideas. So this right here is a representation of a set called a deterministic finite automata, or a DFA. Now, let me explain how to read this picture. So, I'm sort of overloading you a little bit, right? What do these words mean? What does this picture mean? We'll break them down, okay? So in this picture, there are two kinds of things. The first kind of thing are the circles. Those are called states. In this case, we could label them. Let's label this one A and this one B. Notice that there are exactly two states. That means that the set of states is a finite set that contains just A and B. That is why these are called deterministic finite automata, because the states are themselves finite. Now, one state is very important. Inside of the box of the automata, there's one state that has an arrow coming in from the outside. There's an arrow coming in from the outside. That's the start state. In this case, the start state is A. There's always exactly one start state. Next, some of the states have two circles around them, like that one right there. So if a circle has two states around it, we call that an accepting state. It's possible for there to be many states that are accepting, so that is a set. In this case, it's a set that just contains A. Now the next thing is that there are arrows, and arrows always connect two states. Sometimes the states are the same one. For instance, right here, A is connected to A. And there's always a label on top of the state. Oh, sorry, on top of the arrow. These are called transitions. And we can draw a little table that shows us all of the transitions. So we'll have A and B on one side. So these are the states. And then we can then have on the columns the different possible labels, 0 and 1. Now, what happens A and 0? Well, we have it's labeled with A and 1, the other side is B. B and 0 is B, and B and 1 is B. So this table right here has all of the transitions. Okay, so now that we have words to describe each one of these, let's look at the next part, deterministic. The reason it's deterministic is because this table is always has exactly one thing inside each cell. Later, we'll look at other kinds of automata that don't have one thing inside of here. Those will be a special kind of automata. And automata is just a fancy old-fashioned word for computer. So nothing too exciting there. All right. Now I told you that this picture right here, this DFA, is a set. Well, because it's a set, that means that it has to answer the question, when is something inside of it? So for instance, we can ask the question, is epsilon inside of this? And the answer is yes. And why is the answer yes? Well, I can figure that out by saying, okay, epsilon is a string that has nothing in it. So I look at the starting state, and since there's nothing in it, I look and see if the state that I'm pointing at is accepting, and it is, so I say yes. Then I can ask the question, is 0 inside of it? And what I do is I point at the starting state, then I see that there's a 0, and I follow the 0 edge back to A. Now the string is over, and I'm at a state that's accepting, so I say yes. I can ask the question, is 1, 0 inside of it? Well, I point at this starting state, I follow the edge that says 1, I follow the edge that says 0, I look at where I got, there's no accepting there, so I say no. What about 0, 0, 0? Well, I point at the starting state, follow it on 0, follow it on 0, follow it on 0, and here I'm at a state that's accepting, so I say yes. So it's hard to know. It's hard. We don't have a way of proving that this always accepts everything that's all zeros. But I hope that you can look at it and convince yourself that that's right. Now there are lots of other example DFAs that we could draw. Some, in fact, that we could draw for the exact same language. So let's flip the page and draw another DFA that also is for only zeros. So we'll come into an accepting state. On a 0, we'll go to this state. On a 0, we'll go to this state. On a 1, we'll go here. On a 1, we'll go here. And on a 0 or a 1, notice that I'm using a new notation here. I'm putting a comma and writing two different symbols just so that I don't have to have so many arrows. So this machine right here, we call DFAs machine sometimes, is also for the only zero language. In the future, we'll be able to prove that this DFA and this DFA right here accept the same strings, i.e. say yes to the same strings, but right now you'll have to sort of trust me on that, why that is the case. You can kind of see that no matter where the 1 goes, you still get to this other one right here, and this 0, it's almost, it could be like merged into there. You can kind of think of it like that. All right. Now, only zeros is not a very exciting machine, but we can make machines that do things that are slightly more interesting. So for instance, here's one that recognizes evenly long strings. So these are ones that have an even number of digits in them. So we come to an accepting state, because 0 is even. Then, no matter what we see, we go over to here, and no matter what we see, we go back to there. So on a 0 or a 1, on a 0 or a 1. So, we would start here. So imagine that we were given epsilon. We'd start there, and it would say yes. If we got 0, it would go here and say no. If we saw 0, 1, it would go there and come back and say yes. And if we saw 1, 0, it would go there and come back and say yes. So it always says yes to things that are evenly long. What's another one that's mildly interesting? So we could have a machine called the Argh machine. And so what this is going to do is it's going to accept input that are normal letters, like English letters, and it will accept anything that is okay. So what it is that we'll come here and we can have any number of A's, and then we have to have, whoops, sorry. Let's erase this, for goodness sake. Okay. All right. So we start here, and we have to have an A. Then we can have any number of A's, and then we see an R. And then we can have any number of R's, then we see a G. Then we can have any number of G's, and then we see an H. And then we're going to accept here, and we can see any number of more H's. Now, you may ask, what happens if we say an A there, or a G over here? It would be very tedious to write in arrows for all of the other Roman letters, so we're just going to ignore those. And in situations like this, when we leave something off, we're just going to imagine that there's another state that's called fail, and it loops back on itself on anything, and then there's just edges to it from everything else. This is just a convenience so we don't have to worry about these all the time. So this machine right here will accept strings like Argh, okay, because we see A, R, G, G, H, H. Okay, so Argh. Okay, so there are a wide number of different strings. So each one of these machines that we've written so far, in fact, always they are infinitely large. The number of strings that they accept is infinitely large. We can, however, write down DFAs for finite languages too. So for instance, what if we wanted to write down one for just 0, 1, and 0, 1, 1? How could we write down that? Well, we would come in. If we saw a 0, we would go to an accepting state. If we saw a 1, we would go here. If we saw a 1, we would go to an accepting state. And if we saw a 1, we would go to an accepting state. So this right here is a machine that recognizes 0, 1, and 0, 1, 1. All right. So we've seen quite a few examples of different DFAs, and now it's time to formally define them. I've intuitively told you what it means for something to be inside, but now I'd like to give you a formal definition of that. What we want to do is define what it means for x to be inside of a DFA. But now to do that, we have to be able to write down mathematically what a DFA is. Now, there's nothing really wrong with saying that the picture that I showed you before is the definition, right? Because that picture is really a graph, and a graph is a mathematical object. Well, traditionally there is a way to write down a DFA as what's called a 5-tuple. And a 5-tuple is kind of like a pair. A pair is got a 2-tuple. It's got 2 things in it. This is a 5-tuple that's made up of these 5 elements: Q, sigma, Q0, delta, and F. Now, what are these pieces? Q are the states. That's the set of different states. Sigma is the alphabet. Q0 is an element of Q that's the starting state. That's the one that has an arrow coming in from the outside. Delta is a function that goes from Q cross sigma, arrow Q. That's the table of transitions. A function is just a way of writing down a table, of course. And F is a subset of Q, which are the accepting states. All right. So when we say that X is an element of the DFA, we're going to be talking about X being an element of the set indicated by this 5-tuple of things. All right. Now, to define this, we're going to use 2 extra ideas. We're going to use something called a DFA configuration. And a DFA configuration is a pair of a Q and a sigma star, i.e. a state and a string. And we're going to write this down in the following way. We're going to write down one of these as QW. So for example, we might write down A011. That would be an example DFA configuration. Next, we're going to write down we're going to use something called the configuration update rule. And the configuration update rule is a function that takes a configuration and implicitly a DFA. Really, I guess it takes that DFA first. And then it's going to return a new configuration. And we would write down these things as Q, W, arrow, Q prime, W prime. And the definition of the configuration update function is very simple. It goes like this, that Qi Cx arrow Qj x if and only if delta of Qi C equals Qj. Now, X is a member of a DFA if and only if Q0, that's the starting state, X, goes to, via the configuration update rule over and over and over again, QF epsilon, where QF is inside of big F. Now I know that that's a lot to take in. You may want to rewind and look at this part a few times. But let's look at an example of this. Being applied. So let's make a new page. So here's an example machine. So let's do the even length one. So we'll call this state A, and it's accepting. And then on a 0 or a 1, we'll go to B. And on a 0 or a 1, we'll go back to A. And we want to ask the question, is 0, 1, 1, 0 inside of that set. So the way that we write this is we write down the start state, which is A, and then we write down 0, 1, 1, 0. So that is the first configuration. We know that that's the first one we're going to look at because that's what this says. Write down the start state and then the string. And then we're going to apply the configuration update rule over and over and over. So the configuration update rule says we look at the first character, which is 0. So we look at the first state and then the first character, 0. So we say, what happens, what does delta of A0 say? And it says B. So therefore, we're going to go to B110. Then we look at the rule again, and we go to A10. The rule again, and we go to B0. The rule again, and we go to A. And then now that there's nothing left, I'm going to write epsilon. Okay. So now we look at our rule, and it says it goes to QF epsilon, where QF is inside of F. So we ask the question, is A inside of F? And yes, it is. It's inside of F because it's double circled. So A inside of F, question mark, yes. Therefore, the whole thing we say, yes, it is inside. Now we could take what we've just written in math and turn it into a program. So imagine that first of all, let's rewrite a little bit programming. So we'll write a function called accepts, and accepts is going to take a DFA and a string, and it's going to return a bool. Okay. So accepts will be called with Q sigma, Q0, delta, and F, and some particular string. Let's write x. Okay. And now what we want to do is we want to call another function that's going to do the configuration updating over and over and over again. So we'll just call that function h for helper. And we're going to call it with the state that we start in. We're going to give it the delta function. Sorry, something's going on weird. It thinks that I'm drawing. Something's up with my tablet. All right. Wonder if maybe I need a new pen tip. All right, D, Q0, and X. Okay, now our H function, our helper, takes the DFA, it takes a state, and it takes a string, and it's going to return a bool. So H is going to be called with Q, sigma, Q0, delta, F, and then it's going to get some state Qi, and then some string W. Okay, and we're going to do a case on W, and there are two situations. Situation 1 is when we get epsilon. If we get epsilon, then we're just going to ask the question, is Qi inside of F? And return that. Otherwise, we're going to get Cx, in which case we're going to call the helper function with D, the whole DFA, and then we're also going to give it the delta function called on Qi and C, and then X. And so this right here is a little definition of the function that will take a DFA, a string, and return a Boolean that says whether or not the string is in the language. Now, how might you convert this, this pseudocode right here? Well, it's kind of pseudocode, into a language, I don't know, like Java or something like that. So here's how you might do that in Java. So imagine that we have a class that's called DFA. And it's going to have a bunch of fields. So it's going to have a field called Q, a field called sigma, a field called Q0, a field called F or delta, and then F. Then there's going to be a function. We'll call it public bool accepts string X or W maybe. Okay. So then what we want to do is we want to have a little loop. So we'll say there'll be a state called Qi, and it's going to start off as Q0. Then we'll have a while loop that says, while it's not the case, while it's not the case that W is empty. So we'll check to see if W is empty, and while it's not the case, then what we'll do is we'll say that Qi equals the delta function called with Qi and then X dot first. So whatever the first character is, or W dot first, whatever the first character is in the string. And then we'll say that W equals W dot rest, whatever comes after the first thing. And then we'll keep doing that over and over and over again, updating Qi. And then when we're done, we'll return F dot in Qi. And so here what we're doing is we're defining, we'll have an interface for strings where we can see if they're empty, pull off their first thing, pull off their rest. We'll have an interface for sets like F where you can see if something's inside of it, like if you use lists, it can work this way. And so this right here is a little function that does just what we're talking about. All right, so that is a simple way to define DFAs, and we can go back to the beginning and say, why were we talking about DFAs in the first place? Recall that we want to define all the possible languages, and many of the languages are infinite, and so we have to come up with some way of writing down infinite ones, because we know how to write down finite ones. That's really easy. So we write down these infinite ones. A simple way of doing that is with deterministic finite automata, which are these little graph pictures that have states, a start state, that's the one with an arrow pointing at it, accepting states is the one with two circles, the transitions, which are the labeled edges, which we can write down as this table. There are lots of examples of these. This one has only zeros, this one is evenly long, this one is the strings that are screens, there are ones for finite ones. And we can define the semantics of these with the following mathematical definition. The DFAs are really these 5 tuples, that we can define a configuration, which we write in the following way. The configuration update rule, and then it's easy to say that if we start in the start state, looking at the entire string, and we apply the configuration update rule, and eventually get to some state and no string, and that string is inside of F, then that means it's accepted. We can see that run and build a little function that does it and convert that function into a language like Java. Now, when you define this class in a language like Java, how might you define Q? Well, you could define that with with a list like we talked about last time. Same with sigma. Q0 is, of course, a state element. Delta is just a table, so there's lots of ways of writing a table. You could also write it as like a lambda function. And F is also a also a set as well. So that's enough for today, and we'll come back next time and learn more about DFAs.